So just to start today, what I want to do is just make sure that we're all okay with how we find oxidation number. Because you have to be able to find the oxidation number of an element in order to determine what compounds it will form with other elements. And that's what we're doing today. So let's get a little bit of practice. Find potassium. You'll need your periodic table today out. Find potassium and tell me, Anthony, how many valence electrons does potassium have?
Wait, what are valence electrons?
Valence electrons are just the outermost electrons. One valence electron. So, Anthony, what does that give it for an oxidation number? It has one outer electron, one valence electron.
Plus one?
Yeah, plus one. It's because one extra electron. If it could get rid of that one extra electron, then the next layer inside of that would be full and it would be stable. Finley, find calcium, please. How many valence electrons does calcium have? Two valence electrons. Giving it oxidation number of what, Finley? Plus two. It's two extra electrons. If it were able to get rid of them, then its outer layer would be full.
We put minus 6. I mean,
No.
6.
No.
Where?
Lead. Where is what?
Where's
Calcium?
No, lead.
Oh, lead is over off to the right. PB. So again, it's one of those Latin symbols. That's why it's PB for lead. Amna, how many electrons?
4.
4 valence electrons. So this is one of those where it could either gain or lose 4. And so we can put a plus 4 or a minus 4. It might behave differently depending on what other element it's combining with. How about krypton? Bella, how many valence electrons?
8.
Correct. What does that make its oxidation number?
0.
0. It already has a full outer shell. It's already stable. It doesn't need any other element to combine with it to make it stable. Willa, question?
Does that mean it won't come out?
Yeah, usually those noble gases on that far right, group 18, they already have full outer shells. They generally won't combine with any other atoms. They're inert, we call them. They're non-reactive. All right, last one, phosphorus, Calvin. How many valence electrons?
5.
5.
And minus 3.
Yes, giving an oxidation number of minus 3. It's missing 3 electrons. If it could gain those 3 electrons, then it would be full, and then it would be stable. All right. So when we look at the periodic table, you're going to have to flip ahead like 4 pages. I wanted to do this slide before we get to our compounds. So let's talk about the difference between metals and non-metals. Because they combine often to form compounds together. Right?
I forgot to do this, but how do you know if you should add or subtract oxygen?
You have to think, if it's less than 4 electrons in the outer shell, it's positive. Basically, the atom is going to do whatever is easiest. So if you're under 4 electrons in the outer shell, it's easier just to get rid of them. So it has a positive oxidation number. If you have more than 4, it's easier to gain them to reach 8. So it's just sort of whatever is easiest. So the metals on your periodic table are elements that have less than 4 electrons in their outermost shell. They have less than 4 valence electrons. Those are what we consider metals. And nonmetals have more than 4 valence electrons. So metals basically want to lose those outer electrons to obtain a full outer shell. And then how about nonmetals? What do they want, Bella?
Okay.
They want to gain to get to 8. Tell me about oxidation number for metals. Since they have less than 4 electrons, their oxidation numbers are what?
Positive.
Positive. And nonmetals have a negative oxidation number. They're missing electrons. And generally they have different properties. Metals, this is bismuth, it's a metal. Metals are often shiny. They're malleable, which means you can sort of hammer them into a certain shape. They are ductile, meaning you could stretch them out into a thin wire. I'm sure you already know metals are good conductors of heat and electricity. Nonmetals are not malleable and ductile. They are brittle. They break. They're dull. They're not shiny usually. They're poor conductors of heat and electricity. I'll change that, I'm sorry, to poor conductors of heat and electricity. And generally, when elements are combining, 2 elements are combining to form a compound, metals and nonmetals will link up with each other. Metals want to lose electrons, nonmetals want to gain electrons. And so they combine with each other so that they each become stable. Then there are some elements which are sort of in between. We call them metalloids. Okay? They have some properties of metals. They're sort of intermediate between metals and nonmetals. Sometimes they'll combine with other metals, sometimes combine with other nonmetals. So they vary. On your periodic table, there's sort of this little stair-step area. Sometimes on periodic tables it's already drawn in for you. You could draw it in there. That little stair-step is kind of the dividing line. Metals are on the left of that line, nonmetals are on the right, and those things highlighted in yellow, those are the metalloids.
So can we do this on our periodic?
Yep, you can do it on yours, that's fine. Excuse me?
A lot of metals.
Yeah, there's a lot more metals than nonmetals. And some textbooks and stuff will consider aluminium and carbon metalloids. Some don't. It's sort of not a hard and fast rule about exactly whether or not they are. All right. So now, based on what we know about oxidation number and the properties of metals and nonmetals, we can figure out how different atoms combine with each other to form compounds. Because often metals and nonmetals combine to sort of make each one of the elements stable. So let's look at water, for example. We can now understand why water's formula is H2O. Okay. Hydrogen has 1 electron in its outer shell, giving an oxidation number of +1. Okay. Oxygen, how many electrons in oxygen's outer shell? 6. Giving an oxidation number of what? -2. It's missing 2 electrons to get to 8. So, hydrogen's +1, oxygen's -2. When all of those atoms combine with each other, what do they add up to? Yeah, 2 hydrogens, 1 oxygen, and they add up to 0. They're back to neutral, and all of the elements are happy. Each hydrogen can give up 1 electron or share 1 electron, and the oxygen gets 2, making it a full outer shell. And that's why it forms water, H2O. We have this way of figuring out how metals and nonmetals, what the formula will be when they combine. What we do, it's called the crisscross method. We write the 2 elements. We start with the metal on the left, the nonmetal on the right. We write their oxidation numbers above them. Now you're going back. And then we do this crisscross. We take this 1 and put it down here. We take the 2, we ignore the sign, and put it over here. And what do we end up with? H2O1. In chemistry, we don't write the 1s. We assume that. So H2O. 2 hydrogens combined with 1 oxygen, everything becomes stable. That's not how we write it down in chemistry. We use subscripts. All right, let's look at a couple other examples. Sodium and phosphorus. Sodium, which one's the metal, which is the non-metal?
Sodium's the metal.
Yeah, sodium's the metal. It's on the far left of your periodic table. What's its symbol? Na. Phosphorus is P. That's the non-metal. Emily, how many electrons in sodium's outermost shell? 1. So what does that give it for an oxidation? +1. Ryan, what is phosphorus? How many valence electrons? 5. What's that give it for an oxidation number?
-3.
Yep, -3. We do our little crisscross thing. We ignore the signs. The 3 comes here, the 1 goes there. And we get our formula. When sodium and phosphorus form a compound, they have the formula Na3P. 3 of these sodiums combined with 1 phosphorus, forming a compound, sodium phosphide.
Is that, what is
Yes.
that compound?
Yeah.
That's-
Alex?
So say if it wasn't like +1 and +2.
Yep.
You just put the 2 next to it.
Yep. Meaning there would be 2 phosphorus and 3 sodium all combined. Calcium and sulfur. You have a question, Willa?
So how is it that some numbers end up like every number has?
It's just those are larger compounds with more than 1 atom. Calcium and sulfur. Calcium. Connor, how many valence electrons in calcium?
2
2. Giving an oxidation number of what?
+2.
Yep. How about sulfur? How many valence electrons come?
-2.
Well, yeah, how many valence electrons are there?
6.
Yep. Giving an oxidation number of what?
-2.
-2. Is there a little crisscrossy thing? Calcium 2, S2. And we could also usually simplify that. Because they're both 2s, we can simplify just CAS. Like a fraction. 2 over 2 is 1 over 1. Okay, let's do 3 more and then we can start our homework. Beryllium and fluorine. Anthony, find beryllium. Got it? How many valence electrons?
+2.
How many valence electrons?
2.
Yeah. Give me an oxidation number of.
+2.
How about fluorine? How many, what's its oxidation number?
-1.
Yes, -1. We're crisscross. And we get BeF2, beryllium fluoride. Magnesium and oxygen. Alex, magnesium, how many valence electrons?
Oh, 2.
2, give me an oxidation number of what?
2.
Yep. How about oxygen, how many valence electrons?
6.
Oxidation number?
Minus.
Yep. So our crisscross, Mg2O2, and we could simplify that. Magnesium oxide. And finally, barium chloride, barium and chlorine. Megan, can you find barium, please? Periodic table.
BA.
Yep. What's its valence? How many? Actually, how many valence electrons?
2
Oxidation number?
plus 2.
Correct. How about chlorine, Megan? How many valence electrons?
7
Oxidation number?
-1.
Correct. Crisscross applesauce. Barium chloride, BaCl2. Pretty simple, right? And this is how you determine some of the possible combinations when metals and nonmetals combine. Calvin?
This might sound like a dumb question, but anytime you said like what the compound was, it had both of the names.
Yeah, we'll talk about naming of usually metal, non-metal compounds. We just say the name of the metal and then the name of the non-metal, but we change the ending to I. Like carbon dioxide or magnesium oxide, beryllium fluoride, barium chloride. There are other rules when you name other types of compounds because metal, non-metal compounds are not the only types of compounds, but we're not really going to get into much. Anna?
Can you go back to the slide? I just need one more bullet point on number.
The metals and non-metals?
Yeah.
Yep. All right, so I'm going to give you your homework. It's basically just do some practice with these metal, non-metal compounds. There you go. Oh, no. Okay, so it's just the back of this. And check it tomorrow, go over it, and then we'll move on.
Just in the back.
Yeah, well, the back front is just an explanation. It's basically just what we had in our notes.
So then in back.
It is only what I feel we need. Nothing to do on the front. I guess you guys could probably finish it. We'll be close.
Wait, so. Oh,